Okay, got one definition and two theorems on the board. This last theorem is the one we're sort of building to, and it's the one I referred to at the end of the last video. Okay. First, the definition. C is a critical number for f if C is in the domain of f. Now that just means that f of C is defined. So I get a point at C. Okay. And the derivative at C is either 0 or the derivative does not exist. So a critical number is going to be a place where the derivative is 0 or undefined. I should just caution you, the previous textbook we had referred to these as critical points instead of critical numbers. I'm going to try to use the word critical number. I actually think it's the better term because it is just a number. It's not a point which would have an x and a y value. It's just an x value. Okay. But if you hear me saying critical point, I'm using that interchangeably. It's just my habit. Okay. Now, Theorem 7 tells us why we care about them. Theorem 7 says that if f has a relative extremum, and that's just a generic word that means max or min. Okay, so if we have a relative max or min at C, then C is a critical number for f. Okay. So that's why we care about our critical numbers. Critical numbers are possible locations of maxes and mins. I do want to emphasize the word possible. Just because it's a critical number doesn't mean it has to be the location of a max or a min. But if I'm looking for maxes and mins, that's a place that I definitely want to look. Now, there's another theorem in your text. It's theorem, Fermat's theorem. And it just says if f has a relative extremum at C and the derivative is defined, then the derivative is 0. Okay. That's an important theorem. I didn't bother to write it on the board because I think it's covered by 7. 7 says if there's a relative extremum, then either the derivative is 0 or undefined. Fermat's theorem just says, oh, and if it's not undefined, then it's got to be the other possibility that it's got to be 0. Okay. All right, excellent. And then Theorem 3, the extreme value theorem, tells us that if f of x is continuous, that's a very necessary condition, on a closed interval from a to b. That's also a necessary condition. Okay. So it's got to be an interval that includes the endpoints. Now, a consequence of that is that it has to be a finite interval, because we know if we go off to negative infinity or infinity, we can't include those endpoints because they're not actually numbers on the number line. So it's got to be a finite closed interval. But if we have a continuous function on a finite closed interval, then it achieves an absolute max and an absolute min on AB, on that interval. Okay. We're guaranteed that there's going to be an absolute max and an absolute min. So we had some functions earlier where we didn't have absolute maxes and mins. Whoops, I threw away the wrong marker. But they didn't satisfy these conditions. Either the function wasn't continuous or it was defined on an interval that was not a closed interval. Okay, whoops. Okay. So how we're going to use this is if the extreme value theorem tells us for sure that there's an absolute max or a min, there are two locations where it could occur. Okay, so could occur at endpoints or critical numbers. Because if it occurs at a point that's not an endpoint, then it occurs at some point where the function's defined on either side, so that if it's an absolute max or min that occurs in the middle of this interval, it's also going to be a relative max or min, and then Theorem 7 kicks in and tells us we're at a critical number. So let's take a look at an example and see how we can use this fact to actually find the location and the value of an absolute max and min. So I'm going to take a look at the function f of x equals x e to the x on the interval from -10 to 2. So notice I'm restricting the domain. I'm not looking at the function on its natural domain, which would be all real numbers. I'm just looking at it on this finite closed interval. That's definitely a continuous function, so I know for sure that an absolute max and an absolute min exist. I'm going to find their location and value. So here's what I'm going to do. I'm going to create a table of values, and in the column for x, I'm going to list the possible locations for the max and the min. So that would be my endpoints. That's -10 and 2. And then I also have to check any critical numbers. Okay. So let's see. If x is -10, I'm going to get -10 e to the -10, which is -10 over e to the 10th. If x is 2, I'm going to get 2e squared. Okay, now I also need to check critical numbers, so for that I need to take the derivative. So f prime of x, looks like we're using product rule. So it's the derivative of x times e to the x plus x times the derivative of e to the x. Derivative of x is just 1 times e to the x plus x times the derivative of e to the x is e to the x. I want to know where this thing is either 0 or undefined. Now, when I'm looking for critical numbers, I always look for places where it's undefined first. The reason is that's rare. A lot of times we're going to get something like this, where this is always defined. AD is the abbreviation I'm going to use for the rest of the semester. That means always defined. By writing that, I'm indicating to myself that I looked, I checked, don't have any critical numbers because the derivative is undefined. The reason I check that first is because a lot of my derivatives will be always defined. And so I could forget to check for those. And I could get away with that for like 5 problems in a row. And then suddenly the 6th problem, the absolute max or min occurs at a critical number where the derivative is undefined. And I don't find it because I forgot that I had to check for it. Okay. So I just make it my habit to always check for that first. And then, so I don't get any critical numbers from it being undefined, but I want to see when is this thing equal to 0. Well, what's lovely about using product rule when there's an e to the x or any exponential function involved is that the exponential function shows up in both terms so that I can factor it out. Now, if you remember when we were learning all of our derivative rules, I said I wasn't super picky about how far you simplified your derivatives. And I mentioned that there were going to be times when we were going to do things with the derivative, and that would incentivize us to simplify in a particular way. Here's what I was talking about. If I'm setting something equal to 0, it's a whole lot easier to solve if I can get things into factored form. Okay? So I want to be on the lookout for that anytime I'm looking for critical numbers where the derivative is 0. Because then I know that if 2 things multiply to give me 0, one of them is equal to 0. So either e to the x is 0 or 1 plus x is 0. But I know that e to the x is never 0. So that's not going to give me any solutions. And if 1 plus x is 0, well, x is -1. Okay. Now, I do need to check that -1 is actually in this interval. If we'd been working on the interval from 2 to 10, this would be a critical number that I didn't care about because it wasn't in the interval for the problem. But -1 is in this interval. And when x is -1, I'm going to get -1 e to the -1 or -1 over e. So now I've listed all of the possible things that could be locations and values of maxes and mins. All I need to do is look at these y values. The biggest one is the max, the smallest one is the min. Okay. Well, 2e squared is the only one that's positive, so I know that that's the max. Usually, though, the way I phrase the question is the way I phrased it here. Find me the location and value. Okay. So just writing that isn't sufficient. I want you to distinguish between what's the value and where does it occur. So I would write out in words, f has an absolute max of 2e squared. It occurs when x equals 2. So that's the value, that's the location. Now, these two numbers are both negative, so I just want to know which one is the lowest down. Now, obviously, if you're doing the homework, you've got access to a calculator. You could just plug in and get decimal approximations. But we should be able to figure this one out without a calculator, by just sort of estimating. Here, my denominator is e, which is between 2 and 3. So this is between a half and a third. My denominator is e to the 10th, which is somewhere in between 2 to the 10th and 3 to the 10th. My denominator here is huge, which means this fraction has a really, really small absolute value. This is going to have the bigger absolute value, so it's more negative, so it's going to be my min. So then I would write f has an absolute min of negative 1 over e. It occurs when x equals negative 1. All right, so that's pretty much how we're going to be using the extreme value theorem. What I'm going to do now is I'm going to put another problem up on the board. I'm going to end this video so that you can turn it off. Try this problem before you come back to the next video. In the next video, we'll work it through it together, but try it on your own first. Okay. So I'm going to let f of x equal x times sine x on the interval. No, I don't want x sine x, I'm sorry. I wanted e to the x sine x on the interval from 0 to 2 pi. So that's a continuous function. That's a finite closed interval. I want you to find the location and value of the absolute max and min. And in the next video, we'll work through it together.